these are when I say concept, these are all things that have to do with the details about what's in an image file or in image data. So the first thing that comes up very frequently is coordinates, and there are lots of different types of coordinates, but the simple kind of coordinate is relative to the corner of the image. And sometimes we call this like XYZ coordinates or sort of image file coordinates. There's probably some technical name for it that I've never heard. And this just really has to do with the way the data are stored in the file. And the X, Y, and Z coordinates, they don't have any correspondence to anything in the real world. So it could be that the X-axis is left-right. The X-axis could be anterior-posterior. Turns out that conventionally, and for images that are stored in, especially images that are stored in files in meant to be in axial format, or that have been acquired axially, the X dimension, the X-axis is left to right, the Y-axis is anterior-posterior, and the Z-axis is inferior-superior. So that turns out to be the most common orientation that people assume when you're looking at functional imaging and lesion analysis. But there are always exceptions. There are always groups that do things differently. The other thing that's often confusing about coordinates is that even when you know the relative of the corner, the question is, what voxel is the corner voxel? Is it 0 or 1? And the correct answer is 0, but unfortunately, sometime around 15 years ago, SPM decided that they were going to number everything from 1. I guess because that's is that a more natural way to do it in MATLAB? I don't know. The result of which is that right now SPM, which is the sort of 800-pound gorilla in image analysis, assumes that the corner voxel is 1, 1, 1, whereas basically every other software package, or most of the other software packages assume, including Voxpo, assume the corner voxel is 0, 0, 0. The bottom line is it's something to be careful about and to make sure you understand the coordinate system of the software you're using.
Also, the image coordinates are not the same as MNI coordinates, which is important.
Right. So these are coordinates relative to the corner. The coordinate and they're in units of voxels. So the next voxel over has coordinates. If the corner one is 0, 0, 0, the next voxel over is 1, 0, 0, and 2, 0, 0, and so on. And eventually you run out of data in that row, and you go into 0, 1, 0, and so on. You can also look at coordinates relative to, I wish I had relative to the origin of the image, which is an arbitrarily set voxel that's used to establish a coordinate space. So that I guess that sounds circular the way I said it, but the reason for selecting an origin is so that people can have images of different sizes and dimensions that have the same reference point. And the most popular and common example of this is template space, which is usually MNI space, which is kind of a flavor of Telerik space. And in the context of MNI space, the origin is is a voxel that's supposed to be right on the anterior commissure, and actually sometimes is, but generally speaking, in almost all versions of the MNI templates, you'll see it's actually a little bit north, a little bit superior, and probably a little anterior too, of the anterior commissure. I don't know why somebody did it that way. That's the way it worked out. I think it's actually due to some long ago historical conversion of a bunch of images to Telerik space. There is now floating around, however, a set of brain images that are, by all other measures, in MNI space, but actually have a corrected origin that really is smack in the middle of the anterior commissure. At this point, I don't know who to blame for this situation. But the point being, once again, that you need to understand the coordinate system that you're looking at and report it correctly if you're reporting articles. I should mention that although one's derived from the other in some ways, MNI space and Telerik space are not the same thing. There are some systematic differences owing mostly to the fact that the Telerik Atlas, which is a book, first and foremost, is an atlas of one person's brain, probably not a very typical brain for most of the populations we're looking at, or maybe this doesn't matter, but MNI MNI space is in many ways a very similar space. So if you use MNI coordinates to look things up in the Telerik atlas, you'll get something that's pretty close. In some cases, so close that it doesn't make a difference. But in other cases, not so close that it doesn't make a difference. There are transformations available to convert MNI coordinates to Telerik coordinates. And again, it's important to be careful when you're reporting coordinates, to be very explicit about where those coordinates were derived from and what transformations were applied to them. So the second line here, I have these 6 letters that are often used to help orient you to the space of an image. They stand for left, right, anterior, posterior, inferior, superior, and it's frequently helpful if you want to describe how an image is stored in a file to refer to it in terms of these 3 letters to describe where the first voxel is. So, for example, an image that is in RPI means that the first voxel is the rightmost, the posteriormost, and the inferiormost voxel in the volume, which is typically the way these volumes are. So if I open up this, I already have it open, I guess. If I open up this column brain and I go to the 0, 0, 0 voxel, you can see I'm going all the way to the left, all the way to the back, and all the way to the bottom. So this image was stored in RPI. I guess well. So I happen to this really is LPI, right?
I'm not sure.
Oh, so the column brain actually I'm assuming this version is flipped, so actually left is right. So even though the image is stored as RPI, it's stored as RPI. So that when we go to the leftmost voxel, we're actually seeing the rightmost part of this person's brain.
Some people talk about like left-handed coordinate and right-handed coordinate. Are they relevant to any file type or?
Left-handed, right-handed, what? Sorry.
Some people say left-handed coordinate and right-handed coordinate.
You're covered.
In terms of orientation, image orientation.
Left-handed, right-handed.
And
I don't know what that means.
right,
This is why I really sort of feel like, when somebody tells me something about orientation, I usually ask a lot of questions because, frequently image volumes have been through a lot of transformations by the time. And it turns out to be a much simpler problem, much easier problem for lesion analysis because you usually know something about the distribution of your lesions, whereas if you're looking at fMRI data, the best you can hope for is that maybe you have a task where somebody gives the right hand a lot, and you can sort of spot that pattern. But yeah, I don't know the answer to that question.
I don't know whether this is related to my previous question, but the most frequently observed phenomenon that I had a while ago was when I load up an image in MRI Crow, and then it looks fine to me, and then if I load the same image in MRI Cron, then only the Y direction is kind of reversed. Is it related to any coordinate system or something?
Well, yeah, so one of the things that happened the big thing that happened between MRI Cron and MRI Cron was NIFTY support. And MRI Cron, makes an effort to support NIFTY orientation information, which is stored in the header. MRI Crow doesn't. So MRI Crow basically does the same thing that the VoxPose viewer does, which is, it gives you the x-axis from left to right, the y-axis from, this way, and the z-axis in slices. I think you can turn it off in MRI Cron, but I think by default it tries to make use of that orientation information to show you the image correctly. So in fact, you can see worse things than left-right flipping. You can see things like getting shifted if you're not careful. Sometimes that's actually what you want when you have images that have an arbitrary spatial relationship. Sometimes it's not what you want. Yeah, back in the old days of fMRI, they used to put people put like a little some sort of marker, usually I think a vitamin E capsule on the side of people's heads, so you could always sort of get an idea which was left. But as far as I know, nobody does that anymore. Nobody around here anyway. So, whoops. The other thing that I have here is voxel sizes. This is fairly straightforward, but voxel sizes tend to range from about 1 by 1 by 1 millimeter to 3 by 3 by 3 millimeters. Sometimes they can be bigger for different types of data, but those are typical of what we see. 1, 2, or 3 millimeters squared. Obviously, that affects how you understand where you are in the image. So if you're looking at image coordinates, sort of the volume coordinates, the third voxel is 3 voxels away from the first voxel, but it's you don't know how many millimeters unless you know the voxel sizes. So when you're talking about where you are relative to the origin, obviously the number of voxels you are and the number of millimeters you are is different. Typically, when you're talking about origin relative to voxels, it's fairly unusual to talk about that in voxels, except in the one specific case of when you're talking about bounding boxes, which I'll get to a little later. I don't need to talk about image dimensions. We already talked about origins. Okay, so the next concept that I have on here that I just want to explain because it's going to come up a million times is that of image space. And I think the word space means a bunch of different things, but there's one particular meaning that I think is very helpful, which is that when 2 images are in the same space, the voxels that are in the same origin relative coordinates, the voxel that's right at 10 millimeters to the left of the origin is the same in the 2 images, or is reasonably close. So images that have been transformed into M&I space as well as possible should basically have everything in the same space once you've taken into account the voxel sizes in the origin. So 2 images that are in the same space can have completely different dimensions for the volume. One can be 1 millimeter voxels can have 181 by whatever, it's 217 by 181, which is a typical 1 millimeter M&I space volume. The other one can be 53 by 63 by 47, which is a 3 millimeter volume that we frequently have in the past used for normalized functional data. Those images, just because they have completely different dimensions and voxel sizes, they're still in the same space in the sense that if you try to get to the same place relative to that origin in both those volumes, you should land on the same structure to the extent allowed by the image resolution. In many cases, when you're talking about normalizing data, which is what we're talking about today mostly, that space doesn't end up exactly the same. But generally speaking, when you're talking about M&I space, you're not talking about voxel sizes, you're not talking about image dimensions, or field of view, or any of this other stuff. You're really talking about getting the images to the place where the same structures are locatable by the same relative coordinates. I'm going to skip talking about bounding boxes because it's irritating and we'll probably run short of time if I don't. But the last thing I just want to mention is transformations. So as I mentioned a few minutes ago, Nifty files come with spatial transformations that are stored both in the header or sometimes alongside them in separate files. Actually, if they're stored in separate files, it can be any file format can have these transformations. What do these transformations do? For the most part, the ones that are stored in Nifty files are what are called affine transformations, which basically encode a very limited set of transformations that basically includes rotating, translating the image, flipping it,